Good morning, mathematicians. Hope you're all doing well, and that you've been proving things this weekend. Okay, I guess I probably shouldn't start the beginning of my office hours always with dead silence. Probably a bunch of people have clicked away already if they're watching the recording afterwards. I already was looking at Reddit a little bit while I had breakfast, and there wasn't any crazy news I was seeing. So I don't know how to get this party started today. I guess I just keep yapping about what I was yapping about last time. Well, last time I was yapping about cohomology. But I'll go back to slowly yapping through my research. Where were we? Yeah, we had this table. And I made the claim that these two orderings, so we had this ordering on the combinatorial gadgets called multisegments, and we had also an ordering over here on the orbits that were upside down from each other, and I was going to claim that this isn't a coincidence. And then I took the numbers that define the multisegments and I wrote them down over here. So maybe I'll keep describing that for a moment. So if you remember this ordering of orbits, what was the variety it came from? So it was this. It was a variety which was just isomorphic to A4, or just C4, if you will. And but it looked like this, and our orbits corresponded to the ranks of these two submatrices, if you will, and their products. Well, what's the connection here? So the connection is these are the numbers defining the multisegments, right? Over here in the top. And so what we're going to do in general, remember these are supposed to be representations of a p-adic field, well, GLN of a p-adic field. What we're going to do is take the matrix S, and this will be the diagonal matrix, which is Q to those corresponding powers. And now what you do is you consider conjugation on the full Lie algebra. So let me say this. So we're looking at representations of GLN, in this case GL4QP. I'm going to define S, and I'm going to think about this as an element lying in GLNC. I wonder if chat's being weird again, if I have to restart chat. Normally someone's popped up by now to say hey, but it is a Sunday, so oh, it does say 3 watching, so oh yeah, okay, see, yeah, chat was being weird again. Good morning. Just got to get myself reorganized here. And then I'll keep yapping until the questions roll in. Oh, good morning, person. So, so S we're going to think of as an element, but instead we're looking at GLN over the complex matrices. Then we take the Lie algebra, which is just, 4x4 matrices. We take the Lie algebra, which is just all 4x4 matrices. And then conjugation by S, so we call that add S sometimes. This is a linear transformation from the Lie algebra to itself, right? Just conjugating matrices. And then what we're going to do is look at, the Q eigenspace. So we take this the P eigenspace. So GP is the P eigenspace of add S. So literally you just conjugate, you look at a conjugation of a good morning, William. You look at what happens when you conjugate an arbitrary matrix by this thing. When you do that, you'll see a bunch of powers of Q show up, and you just look at the entries where you see Q. And it turns out that the Q eigenspace is exactly this thing. So this is the connection between these two. Well, this is the beginning of the connection. This is where it starts. So we also had, one of the things that we computed was not just the structure of the orbits, but we computed stalks of certain perverse sheaves on here. And so here's the general, again, understanding we've made some simplifying assumptions here, but roughly speaking, the p-adic Kazhdan-Lusztig hypothesis for GLN over a p-adic field says this. It says, let A1 through AN be some collection of half integers. Then the claim is that hello mushroom. Hello mushroom. Our claim is that there is a bijection. So how should I phrase this? So okay. Suppose we have these numbers. Define S as we did before. So maybe let S. We could choose these in any order. Let's just suppose, for example, that these are monotonically decreasing. It doesn't really matter. It just makes the computations nicer. The order, the order shouldn't matter though. Let S be this complex matrix, and consider the Q. So G. So this is the P eigenspace of conjugation by S, where G is the Lie algebra of the complex version of GLN. Oop, didn't mean to pop up there. Yeah, for people just joining, I'm yapping about random stuff to do with my research until people have other questions. So feel free to ask any of your random math questions in chat. So, we've got, where are we here? Got this Lie algebra. We're looking at the eigenspace. And by the way, I guess one other thing I didn't mention, I didn't explain where these orbits came from. So I keep calling them orbits, and before I just called them strata. I defined strata for you. But here's why I kept slipping up and calling them orbits. is because there is a group acting on this. So define H sub s to be everything in GLN C, such that it's fixed by conjugation by S. And now this group HS acts on this P eigenspace, and it does that, it itself acts by conjugation. So that's exactly, so if you unpack those definitions, and you write down this group HS, and you see how it acts on these matrices, you'll actually recover the rank stratification that I supplied in the office hour where I computed those things. So where does that leave us here? So finally, okay, so here's our setup, right? We have some collection of half integers, and I've basically just given the geometric setup for you here. I've explained how this defines some sort of variety and some sort of partition of that variety into what are ultimately locally closed subsets. But then also we know that these numbers, this defines a multi-segment. Maybe we'll call it a top, where it's just a bunch of singleton segments. And maybe we could let capital pi be the collection of all multi-segments B, where B is obtained by some sequence of simple operations from A. So that's something I was talking about yesterday, the day before, I think both. And so we know that we have representations attached to each of these things. And so first off, the claim is that there's a bijection from pi, the set of multi-segments obtained from A, to the set of HS orbits on the P eigenspace of this Lie algebra. So there's a bijection between these two things. And so, well, I haven't explained why this ought to be true. But now this, I'm articulating a general phenomenon that captures this example that we saw here, that we computed. And things get even better because also I did a computation where I computed the stocks of the perverse sheaves. And now we also have yet another claim, which is this. So define the matrix. Maybe I should also remind you that I defined some representations. So we had the Q, so we had SQA, and we had QB. So the QB, these were irreducible representations. It was 10 p.m. where you are. It is 8:36 over here. It's the morning. I'm having coffee. And this is SQA was the thing that we built that has, it doesn't have to be irreducible, but it will have a unique irreducible quotient, which is the thing we would have called QA. So, and remember, our goal is we were interested in answering the question of what are the multiplicities of the irreducibles in the SQs. So, define a matrix to be M R, so say the representation matrix, B BA, so it's BA entry. Its entries are indexed by multisegments. So its entry, BA entry, is going to be the multiplicity of QB in SQA. Then I'm going to define and, let me write and here, so MR for the representation matrix, MG for the geometric matrix. Let me define MBA to be the dimension of, how should I write this? So it will be the dimension. One way to write this is the dimension as you sum over all the integers of the cohomology, the nth cohomology of the intersection cohomology complex. This was a perverse sheaf attached to the trivial representation on the orbit. So I said that there's a bijection between these two sets. So yeah, so I'll write the bijection of this. A multisegment A goes to some orbit CA. You want some coffee too? Prefer to do math than sleep? Well, you can always do what, like I did last night and just have an unrestful sleep because you can't get your mind off of the math that you're thinking about. That's one possibility. Could always try that. But I do try to. I don't have caffeine after usually after noon. Definitely not after 2 p.m. But even these days, I try to keep it all before noon. Yeah. So it's the IC attached to. I'm probably gonna write this the wrong way. I think B. I should know. This is like the whole focal point of my thesis, but I always have to check my own notes about which way I write the matrices. But I'm pretty sure it's this. So you take the cohomology and you restrict it down to the orbit CA. And this is more or less something that we computed in the stock tables in a previous video. Sorry if this is a stupid question, but you're studying Riemann-Hurwitz formula, and you just want to ask, is the degree of the elliptic curve, as in the standard form 2? Let me get to that 1 second. I'm not totally sure I understand the question. But I'm just about to deliver the punchline here. So I've defined these two matrices and the p-adic Kazhdan-Lusztig conjecture. So not only do we have this bijection of orbits, and by the way, so this is a bijection, and in fact I defined, there's an ordering on the orbits and the multisegments, so it's an order-preserving bijection. And the p-adic Kazhdan-Lusztig hypothesis predicts that in general, the representation theory matrix will be equal to the transpose of the geometric matrix, which is incredible. Yeah, so when I reopened the chat, it started from the beginning of the stream. Oh, and now that message has disappeared. I hope I'm not. I saw something about being 15 minutes behind. I really hope I'm not 15 minutes behind. It could be. Well, then, hello from the future. You all know that the world still exists 15 minutes from now. if that's the case. So that's nice. I'd send you information back in time about the stock market if I could. Oh, he just saw that delay, yeah. That's maybe the more likely explanation. Damn, I thought I could have helped you guys get rich playing the stock market. Riemann Hurwitz formula. So let me see here. I should probably stop accidentally revealing my emails, but I wanted that to be open to remind myself to do my taxes. to email the people who did my taxes last year. Which is fun. Next year I'll have YouTube taxes to do for, the pocket change that I've made. So that's great. Your mistake. YouTube decided to move back in the stream. Yeah. Well, I make a ton of crazy mistakes on YouTube. I don't know if you saw the office hours the other day where I thought I was all alone and I was yapping to myself. And meanwhile, I just needed to restart stream. So. Okay, what do we have here? Riemann-Hurwitz formula describes the relationship of Euler characteristic of two surfaces. Right. Why don't I see the thing that I think is the Riemann-Hurwitz? Yeah, here we go. This is what I remember seeing. And now your question is, you're studying Riemann-Hurwitz, and you want to ask if the degree of the elliptic curves, as in the standard form, 2? Yeah, I apologize. I'm not sure I understand the question. It's been a while since I've looked at this stuff as well. I mean, presumably you're going to have like different... well, I guess the degree is some... total invariant. That bit n in the formula. Formula in the usual form. Well, but I mean, this is a relative. So you mean in the case where you have one elliptic curve over another? Because like this is a relative thing, right? So we assume that S and S prime are Riemann surfaces. So you're assuming that they're both like this is an isogeny of elliptic curves or something? Because what is n? The number n, the number little n is the ramification index. What's big N? Is that just a typo? Is that supposed to be the ramification index? Your university master's program has a class on Lie groups and a separate one on Lie algebras. Your schedule is already full, so you can take at most one of the two. Which would you recommend? Oh, man. That's tragic because, I mean, what better perfect pairing of courses? Well, So this doesn't answer the question which one you should take, but I would highly recommend that you at least, if you can only take one, sit in on the other one. At least just go to lecture and listen to what's happening, because these courses pair together so well that it would really be a tragedy to not attend lectures for both. So I definitely recommend just go sit in on the one that you end up not taking. Yeah, Lie algebras versus Lie groups. Well, why are Lie algebras? Yeah. So sorry, 314 calls. I'm not so sure I'll be able to answer your question. I'd have to crack open a book on Lie theory or not Lie theory, sorry. I'd have to stare in solitude at that equation a bit longer. But, oh, they're not even in the same semester. Oh, okay. Well, in that case, definitely, I see. I thought they were at the same, I thought they're at the same time. You know what? I'm going to say Lie algebras. And here's partly why. I mean, here's what I always say, and I'm not the only person who says this, but the math that is hard is math that has not yet been reduced to linear algebra. That's it. There's math that hasn't been reduced to linear algebra yet, and then there's linear algebra. It's really the only thing we understand, and at the end of the day, that's really what solving math boils down to. Even this thing I was yapping out above, right? What is this really? Oh, it's a transpose of two matrices. And, okay, you could say, oh, well, isn't there some fancy thing going on with cohomology? Yeah, but basically you just plug it into a bunch of versions of the decomposition theorem, and you get a system of linear equations and solve it. Like, all these fancy words, it's just like, yeah, it's linear algebra at the end of the day. So, okay, you'll state the question properly in upcoming office hours, and maybe, you know what, maybe I'll do some homework and I'll read up on Riemann Hurwitz, and maybe I'll compute it between two elliptic curves or something. No promises, but maybe. So we definitely care about Lie groups. Well, maybe I shouldn't say definitely. Like, why should we care? Well, number one is they're useful in physics. Maybe they're not number one, but like as a perhaps somewhat more practical thing, Lie groups are definitely important in real world physics as well as theoretical physics, right? Things tend to happen in the real world continuously. Of course, there's quantum processes as well, but it's also very useful for us to describe continuous motions of things. So it makes sense that we'd want to study groups, symmetries of continuous things, very loosely speaking. You also, it's all linear algebra at the end of the day, exactly. Also, I mean, another reason to care about Lie groups is, let's just say you're fascinated by groups in general, and you want to understand groups in general. And I was ranting at the end of last time that, there's so much more to the class, to group theory than the classification of finite simple groups, right? I was arguing that that's half of the story and it's the easier half. But let's say you just want to focus on that half of the story. And you say, well, we've classified all the finite simple groups, so now we need to move on to infinite groups. Well, where do you start, right? Just an arbitrary infinite group that's very little structure, and it's essentially, undecidable. Like you can't, it's like provably hopeless, actually. So the extension problem for groups is hopeless, but the like classifying like all infinite groups is like provably hopeless, basically. So we should try and look at groups with some sort of extra structure. And, we're geometric beings, so we should probably look at groups with some sort of geometric structure, which is exactly what brings us to Lie groups, right? Also, I mean, another way, so I think in one of these streams I was talking about is how a lot of Lie groups, actually speaking of linear algebra, one of the extra structures we put on a vector space is some sort of inner product. It could be a Hermitian inner product, it could be something like the ordinary dot product, it could be a symplectic inner product, like all of these sorts of things. And many cases, many interesting cases of Lie groups can be defined as the group of isometries of some vector space. So these are invertible linear transformations which respect some sort of inner product. Okay, great. So, I, 10 minutes ago, I said you should take Lie algebras, and then I started yapping about Lie groups. I haven't explained anything yet about why we care about Lie algebras at all. Well, it turns out that much of the structure of a Lie group can be encoded in its Lie algebra. So, to every Lie group, we can take its Lie algebra. This process is many to one, right? So it's definitely not a bijection, but it does form an adjunction. So the category of Lie groups, and here we have taking Lie algebras, and here we have, I don't even know what we would call this. Maybe we could abusively call this exp. Maybe I'll call it E. So it's sort of like an exponential map of sorts. So we go back, and I forget which is the left and which is the right. Let's look. Lie algebra adjunction. Lie group, Lie algebra correspondence. Here it is. Or is it stated as an adjunction? Here we go. Yeah. Well, okay, maybe I stated it a little bit imprecisely. But what is CL group? What is CL group? How's that category defined? Connected Lie groups or something. Which Lie groups share Lie algebras? Great question. Let me touch on that a second. Basically, if two Lie algebras, if there's a covering of Lie algebras, so if let me, how do I say it? So the Lie algebra of G will be isomorphic to the Lie algebra of its connected component. So the Lie algebra only sees the connected component of your Lie group, for example. Is that right? No. Am I lying? Because I thought you get something extra in ON. Am I saying nonsense? You thought the Lie algebra was the tangent space of the Lie group? Yes, that is one of several equivalent definitions. Yes, it's the tangent space of the Lie group. Yeah, that's true. That is true. Oh, didn't mean to go there. Yeah. So, the thing is, well, we do not have an equivalence of categories between Lie groups and Lie algebras. We do have the next best thing to having an equivalence of categories. We have an adjunction, which means a lot of information does get preserved between Lie groups and Lie algebras. So what that means is a lot of the things that we care about, from a Lie group, a lot of information still gets encoded in the Lie algebra. Not everything, right? Because now I'm worried something about this I said is false, but there is something going on here with the connected component. It's like, I think it's at least true. There is some statement that like there's a unique connected, given a Lie algebra, there's a unique connected Lie group that has that Lie algebra as its Lie algebra. Something like this is true, but okay, fact check me, please. And well, why is that any advantage? So even if you just cared about Lie groups, the thing is like groups are kind of complicated, right? I mean, you might think, okay, very few axioms or something, but almost because there's very few axioms, there isn't a ton of structure. And unique simply connected. Ah, that's what it is, right? Yes, because we get this. Right. There's some sort of relationship with Lie groups and like covering of Lie groups. Right. That now I remember. And there's some sort of like, you also get a relation, like you can compute using like the theory of fundamental groups and coverings of topological spaces. You can get some interesting thing about like computing the Lie groups that share a Lie algebra using fundamental groups. This is in Fulton Harris. There's a cool section about this. Richard Borchards goes over the uniqueness of the correspondence in his video series on Lie groups. Okay, awesome, great, yeah. Definitely check out his series. Yeah. So right, simply connected. Yeah, that makes sense. Yeah. So there's by the way, cool stuff going on with fundamental groups of Lie groups. And so why is this some advantage though? Well, I just told you that the only thing we really understand is linear algebra, and a Lie group, or sorry, a Lie algebra is what? It's a vector space equipped with some sort of operation on that vector space called a Lie bracket. So now we can bring all of the tools that we have to bear on Lie algebras, and therefore learn information about the Lie groups that we cared about. So some like big things that are important are like Jordan decomposition is like a fundamental, a theorem of like fundamental importance, as well as doing stuff with like eigenspaces, generalized eigenspace decompositions. Using the tangent space, how can we connect our notion of the group operation on that Lie group to the Lie bracket in the Lie algebra? Amazing question. Let me get to that in a second. Fantastic question. They are super related. So, where am I going? Let's see. Vector space, Jordan decomposition. Oh yeah, so in particular, let me just mention that this also leads to so using Jordan decomposition and eigenspace decompositions on the Lie algebra, this leads us to the idea of root systems, by the way, which has like nice combinatorial classifications. And in particular, so just like in the study of finite simple groups, we might think, okay, well, what are simple Lie algebras? And apparently people don't like agree necessarily on the full like general definition, or sorry, of simple Lie groups. There's like slight adjustments you can make, but generally, whatever our simple Lie groups are, one should hope that there's a definition of what it means to be a simple Lie algebra that then connects those notions. And indeed, there are notions of simple and also something called semi-simple simple Lie algebras. And it turns out that using these tools of linear algebra, we have a very, very nice, beautiful classification of all of the semi-simple and in fact simple Lie algebras in terms of this linear algebra and combinatorics of root systems. So hopefully this so far has been a somewhat convincing pitch for Lie algebras. It's as a means to understand Lie groups. Also, let me just say that and this has to do with what I'm about to talk about. If we have if we have a representation of Lie groups, well, probably we don't just want that to be an algebraic representation, right? We want some sort of homomorphism from our Lie group into GL of some vector space, possibly infinite dimensional. But then the things I'm about to say get more complicated if we're talking about the infinite dimensional case. So, but the point is, if you have some sort of homomorphism, probably we should, ask this to also be smooth. I mean, certainly if V is finite dimensional, this will just be isomorphic to like GLN, R, C if we're doing complex or real Lie groups, whatever. So then we can differentiate that map. And speaking of this notion of the tangent space, right? So we take the derivative of that map at the identity element. I mean, this is so the Lie algebra. One definition of the Lie algebra is the tangent space at the identity. So what do we get? We get some sort of linear map from the Lie algebra to the Lie algebra of GLN, and wouldn't you know it, the fact that this is a homomorphism of Lie groups ends up, you can prove that this ends up being a homomorphism of Lie algebras, and therefore we get a relationship between representations of Lie groups and representations of Lie algebras. But again, why is this so advantageous? Well, down here at this level, right? So like, yes, we're mapping a group, elements of a group into some collection of linear transformations, which is already more advantageous because we understand linear algebra better. But over here, not only do we have a linear transformation, but now both of the spaces in question are vector spaces. And so, I mean, there's just so much more linear algebra going on here that we can do to make our lives easy. Now, where does the Lie bracket come from? What's the connection there? Well, as you might know, if you studied some finite group theory, one of the very important things that we study are conjugacy classes. Hey, I wanted blue. OneNote's not listening to me. We study conjugacy classes of groups, right? So what is this? I mean, basically, for each G, we study the map. So let me call it add G, the map given by conjugation by G. And we look at this as a function from G to G. So we can do this exact same thing for each element G. We can look at add G. Well, I guess I've already written it for a Lie group. What am I doing? Why is OneNote not listening to me? There we go. And what we can do is, again, take the derivative of this map of I guess, like, each of these maps, and look at it as a map on the tangent spaces at the identity. And well, d-ad in general, this is what we call little ad. And how does little ad? I mean, this is exactly what defines the Lie bracket. So little ad x is a map from G to G. So for each x in the Lie algebra, we get a little map add x, and it turns out that this little add x is the Lie bracket. Like, this is the definition of the Lie bracket. So the Lie bracket actually comes, so conjugation, extremely natural thing to consider when studying groups. In general, this is a very useful tool for understanding their structure. So we simply take that idea and we say, well, let's study that in the context of Lie groups. Well, maybe that's very complicated, but we can, differentiate everything to get stuff down on the level of Lie algebras, and that's what actually gives rise to the Lie bracket. So you can see that as a motivate, because you might look at the definition of Lie algebras and Lie bracket, and you're like, okay, but why do we study the Lie bracket? Who cares? This is why. It's basically because we differentiate. It comes from differentiating conjugation. And the linearity of the Lie bracket follows from linearity, Leibniz properties of derivative. Basically. Well, it's bilinear. Well, yeah, it's linear. It's linear. Add x is linear in y, and it turns out it's also linear in x. So this is bilinear. And then all the properties that you get can be proven from these definitions. Yeah. But then you might go and study, and then I mean, we originally started doing this for manifolds, right? Manifolds over R or C. But now that we're down at the Lie algebra level, you could ask, well, what if we study this definition was of a Lie bracket was originally inspired coming from the differential geometry, but now you might take this and say, well, what if I consider like a Lie algebra is just a vector space with this bracket, so I can do this purely algebraically, and now I could consider Lie algebras over any field, finite fields, function fields, p-adics, or their closures, or whatever, all sorts of crazy stuff. Yeah. So I think that's going to do it for today. Yeah. I guess it's time to go prove some more theorems. So hopefully I'll see you all tomorrow. You can tell me about all the amazing theorems you proved this weekend. How about